Hello and welcome to our lesson on continuity. So what does it mean for a function to have continuity, or for it to be what we call continuous? So there's an informal definition, which is what we're going to start with, and then I'll get into the more formal piece of it. So informally, we're going to say that a function is continuous if it looks like the picture we see in that first graph. So if I can trace with my pen, my pencil, my highlighter, left to right forever along this graph without any interruptions, we have a continuous function. Interruptions in your graph would be something like a hole or an asymptote or any kind of other gap that I would have to jump over in order to continue tracing my function. So for example, in picture number 2 here, graph number 2, I can trace up until I get to this hole in the graph. That hole in the graph means the function isn't defined there. So in order to keep tracing my graph where it's defined, I would have to jump over the hole, and then I could keep tracing there. So this graph is not continuous. There is a discontinuity in that hole in that graph. Okay, so that's informally the concept. Informally, we're going to say a function is continuous if it is uninterrupted. Uninterrupted. And again, interruptions would be features in a graph like a hole or an asymptote or some kind of other gap in that graph of that function. So formally, again, those interruptions are things that keep our graph, our function, from being continuous. They are what create discontinuities. And so there are three pieces to the definition that have to hold, and you'll see as we go through some of the examples why we need each of these three to hold in order for our function to be continuous. So first, a function is continuous at C, any point C, which is just some x value, if these three things happen. First, our function has to be defined at C. So in example number 1 here, again, we have a continuous function because at any x value, any value of C, we're defined everywhere, the whole thing, okay? So we have to be defined. And that's precisely why number 2 is not continuous, because at this x value, so this x value here, what is the x value here? -3. Right, at this particular x value, this function is undefined. That's what the hole means there. So f of -3 is undefined, and therefore, if any one of these three pieces doesn't hold, our function is not continuous. So f of -3 is undefined, so we're going to say f of x is not continuous at -3. Okay, now I called this f of x, but I didn't actually label that anywhere, so let me go ahead and stick a label on this graph and say that this graph is f of x. Alright, so our function has to be defined at an x value in order for it to be continuous there. So this graph, again, discontinuous at -3. Also, the limit of f of x as x approaches that value has to exist. So in example 2, the limit does exist. As we're approaching this x value from both directions, right, whether I approach from the right or whether I approach from the left, we are approaching a fixed y value of 4. So the limit exists, but the function isn't defined, okay, at that point. So let's look at an example where the limit does not exist. That's what's happening here. So if I'm looking at f of x, again, let's just call this f of x. Actually, let's call it g of x since I called the last one f of x. So let's say that this function g of x, we were tracing from left to right. All the way through here, we're good, but then I would have to jump up to this other piece of the graph in order to continue tracing. So informally, easy to see that this graph is discontinuous. But what is the reason it is discontinuous? Well, here at we can see the discontinuity is going to be at this x value of 0. So an x value of 0 is where the discontinuity happens, but it's not because the function isn't defined. We have a defined y value there. We can see that not f, but g of 0 is equal to 0. So it's defined. However, the limit does not exist. And so we're going to give that as the reason this is discontinuous, because if I'm approaching the x value of 0 from the left, then we're approaching a y value of 0. If I'm approaching the x value of 0 from the right, then I'm approaching a y value of positive 3. So because the limit of g of x as x approaches 0 from the right happens to be positive 3, and the limit of g of x as x approaches 0 from the left happens to be 0, the limit for the entire function does not exist. Remember, those one-sided limits have to be the same in order for the limit to exist. So this is g of x is not continuous at, how did I say it there? Not continuous at 0, at x equals 0. So that is the discontinuity in that graph. Okay? So 3 pieces to the definition. Our function has to be defined, which we saw the fail in example 2. The limit has to exist, which we see the fail in example 3. And then the last part is the limit has to be equal to the function value. So let's look here at example 4. Now, again, informally, I'm hoping we can see how this is a discontinuous graph. So if I wanted to trace this left to right, I can trace over all this pieces where my function is defined. Now, this function is not defined at that hole. It is defined, but it's defined here. So I would have to jump up to this point to trace and then jump back down to trace here. That's a break in my tracing of the graph. That's an interruption in the graph, so therefore I can see it is discontinuous. So we would say it's discontinuous at 2. But what is the reason for the discontinuity? That's the third piece that has to happen in order for continuity to be there. So the third piece says the limit has to exist and it has to be equal to the function value. So the limit exists here, right? The limit exists if I approach the x value we're concerned with here. The discontinuity is happening at an x value of 2. Okay, if I approach that x value from the right, or I approach that x value from the left, the y value that we're approaching, not in question, right? The y value we're approaching from both directions is 1. So the limit of, let's call this function h of x, the limit as x approaches 2 of h of x is 1. Whether I approach from the left or from the right, that's where the function values are headed. However, if I wanted to find h of 1, not h of 1, h of 2. So the limit exists at 2, but if I wanted to find the function value at 2, it is defined here. So this is where our function is defined. That x value of 2 is defined at a y value of 3. So h of 2 is actually equal to 3. And because these two things are not the same, we have a discontinuity in the graph. Okay, so the informal definition is actually easier for us to use to see that, hey, this is a discontinuity, but then why do we consider it a discontinuity, right? So those 3 reasons that we have here. So we need for our function to be defined. That's what we see, or we see example 2 and failing that one. We need the limit to exist, and that's why number 3 was discontinuous. And then we need the limit to be equal to the function value, which is not happening in that example 4. So let's just go ahead and coordinate these. Example 2 shows a fail there. Example 3 shows a fail here, and example 4 shows a fail here. So, and I've used the word, if f of x is not continuous at c, then it is discontinuous there. And I did not give myself a lot of space to write in that blank, but there it is. Okay, so of all the pictures we're seeing here, number 1 is the only continuous function. So let's call this one, let's see, f, g, h, let's go with j. J of x here is continuous for all x. All values of x, all x values, or we could say over the domain from negative infinity to infinity. We could say that lots of different ways, but hopefully conceptually you understand what's happening now. So informally, an interruption is a discontinuity. Formally, that discontinuity happens because of one of these 3 things. Okay, so In general, what kinds of functions are going to have discontinuities, or what kinds of functions will be continuous everywhere? So in general, what's going to happen, and this is not always, but in general, most of our functions that we're going to encounter are going to be continuous over their domains. So they're going to be continuous for the x values for which they're defined, most of the time. Okay, so polynomial functions, that's exactly what we see in this first example. This is a polynomial. Hopefully you're recognizing that word in that picture. Polynomial functions are going to be continuous for all values of x. So polynomial functions are like y equals x to the first, or x to the second, or x to the third, or x to the fourth, and any combination of those terms added and subtracted together is going to create a polynomial function. And those are going to be continuous for all values of x because the domain for all of those functions is all values of x. I can input anything I want into x and square it or cube it or raise it to the fourth and so on. And so you see these nice continuous curves created for any polynomial function. So when I'm looking at problem number 5, where we're asked to find the interval or intervals of continuity for the function, I know that this is a polynomial function and therefore it's going to be continuous over its entire domain. So there are no discontinuities here. No discontinuities. That's a tough one to write out if I don't sound it out. Or we could say that the interval of continuity is everything from negative infinity to infinity. And I should probably write that out. Maybe I'll abbreviate the next few. So no discontinuities, the interval of continuity. Let me do this. That's my abbreviation. There we go. Interval of continuity is going to be everything from negative infinity to positive infinity. That is the domain for that function, and that is also the interval of continuity. Okay. Now let's say you didn't know that. Maybe you didn't recognize that x cubed is a polynomial function, or maybe you don't know what the picture is going to look like. You do have technology, so you can always look at the graph. So if you were to graph x to the third minus 2x squared minus 5x minus 4, you're going to see a picture similar to the one we saw in that first graph, and again, it is continuous everywhere. As far as you want to go left and right, you're going to be able to trace that without any interruptions. Okay? So polynomial functions, again, good everywhere. If we have a rational function is definitely going to have a discontinuity. Just depends on where and how many. Rational functions are discontinuous because rational functions are fractions of polynomials. And as soon as you introduce a polynomial into the denominator of a fraction, you have the possibility of making that denominator equal 0. And that's precisely where the discontinuities happen. So rational functions, those would be like what we see here, fractions of polynomials, like 1 over x. Those are going to be discontinuous at values of x that make their denominators equal 0. Anything that makes a denominator equal 0 is going to cause a discontinuity in that rational function. So for example, in number 6, again, I know this is a rational function. I know there's going to be a vertical asymptote in this graph at x equals 9, right here, because x cannot equal 9. That is kicked out of the domain. There's going to be a vertical asymptote there. A vertical asymptote happens at x equals 9. So this function is going to have a discontinuity there, but it will be continuous everywhere else because every other x value is in the domain. So this domain excludes 9. It excludes that discontinuity, and it is continuous everywhere else. So we would say it's discontinuous at x equals 9, and the interval of continuity is everywhere else. So everything before 9 united with everything after 9. Okay, so the interval of continuity, again, everything except for that discontinuity. Now again, maybe you don't know what the graph looks like, or you're just dusting off the cobwebs, your algebra's a little rusty, and you couldn't just tell by looking at that what was happening. Graph the function and you're going to see exactly what I just said. So if you graph 1 over x minus 9, here it is. And I can see, and I'm just going to type it in here for you so you can see it. If I put x equals 9 in there, that is precisely where we have our vertical asymptote in this graph. Is not, there we go, got stuck. That's where our vertical asymptote is. That is our discontinuity in that graph. So if I was tracing, not the green because I interjected that, but here's my graph. If I was tracing, I could continue on that first branch, but then I'd have to jump over the vertical asymptote to continue tracing on that second branch. So again, a discontinuity at x equals 9, so the interval of continuity is everywhere else. Now I suddenly feel the need to box some of these things in, so let me do that. And not there, but here. Okay, so we got polynomials, which are going to be good everywhere, rational functions, which will be discontinuous, where their denominators are equal to 0. Exponential functions are another common type of function we encounter. Exponential functions are like polynomials. They will be continuous for all values of x. And that's what we're going to see happen here in example 7. So an exponential function means we have a variable exponent. And just like with a polynomial, I can raise any number to the third power, raise any number to the second power. I can take any base of an exponential and raise it to any power, and an output's going to be produced. There won't be any places where this thing is undefined. Nothing weird happens in an exponential function in terms of x's, and so this is going to be continuous. So I know by looking at this equation it's exponential, so I know there will be no discontinuities. And yeah. No discontinuities, so the interval of continuity is going to be everything. It's going to be continuous everywhere from negative infinity to positive infinity. Now again, if you weren't sure, didn't recognize that was an exponential function, look at the graph and you'll see. If you graph negative 3 raised to the x plus 2 power, I think I need to put parentheses to keep the exponent together there, and then zoom. There it is. Here's our exponential function. And I can trace this thing left and right forever. There are not going to be any issues in tracing, no interruptions in that graph. Okay, now if we look at number 8, we have a square root function. Now a square root function has limitations, just like a rational function has limitations. Rational or a fraction can't have a 0 in the denominator. If we're talking about a square root, we can't square root anything that's less than 0. So square root functions are going to be continuous, again, over their domain. The domain for a square root function is, or includes all of the x values that ensure that the radicand, the thing that's underneath the square root, the radical, is at least 0. So we're going to say that the radicand, I can actually go back to red here, that the radicand for a square root has to be at least, so we're going to say greater than or equal to 0. So a square root function, again, like the square root of x. And let me put this up here. Exponential function means we have some base to the x power. Okay, so square root function, again, I can square root 0 or anything bigger than 0, but nothing less than 0. So I need to make sure that my radicand, the thing underneath the radical, is at least 0. I can square root 0 or anything bigger. That's what this is saying. So if I'm solving this, then I can actually find my domain, which means I can find my interval of continuity. So if I added the 7 over, I see that my x's have to be greater than or equal to 7. That's going to be my interval of continuity. So this function doesn't actually have any discontinuities, it's just only continuous over its domain. So we're going to say that the interval of continuity is, if the x's are greater than or equal to 7, then it's going to be from 7 to infinity, and this time we can actually include the 7. And again, maybe you're just not sure, but let's look at the picture. If I was to graph the square root of x minus 7, here's what my picture looks like. So this is going to be a continuous graph over its domain. So there's no graph, there's no function defined before an x value of 7. So we're going to say it's continuous everywhere in its domain. That's why we had to start this at 7. So from 7, to infinity, we're good, but since there's no function defined before that, there's no continuity before that. Okay. Now piecewise functions are the ones that are a little different. Well, we have to be a little more careful because they can vary each piece is likely, but not necessarily going to be continuous over its domain, and then we might be continuous from one piece to the next, or we might not. So we really just have to be careful with our piecewise functions. The continuity of the piecewise, which is what we're going to see in the last two examples, it will vary depending on what the pieces are and what the domains are for each of those pieces. So let's look here. Now, I know what these functions look like. I even know what this piecewise function looks like. But the only place we would have to worry about an interruption here is going to be at this barrier, or not barrier, but like, oh God, the word is escaping me. So there's a possible break, and I don't know what the word is, it's escaped me, but the possible break in this domain is going to happen at 0, because I have one piece that's going to dictate the behavior for x is less than 0, and then I have the second piece that's going to dictate the behaviors for the x is greater than or equal to 0. So are those pieces are they going to connect and make one continuous piece, or are they going to be gapped or completely disconnected? So let's start by looking at the picture on this one. So remember how to graph a piecewise function. I'm going to put the first piece, which is a polynomial. It's linear. The second piece, also a polynomial. I know the two individual pieces will be continuous, but do they line up each of these pieces? So let's graph x plus 1. Remember, this is for the set. That's why we use the brace there, of x's that are... oh, that's a typo. This should definitely be less than 0. Okay. Don't mind the typo. So there's the first piece, and then the second piece, again, it's quadratic, that's a polynomial, it's going to be continuous everywhere, but let's look at the piece for the set of x's that are greater than or equal to 0, and here we have a discontinuous graph. So if I'm tracing the first piece, I would have to jump up a few units to get to that second piece. So this is going to be discontinuous. The limit is not going to exist here. And so that discontinuity at x equals 0 means our interval of continuity would be everything before that and everything after. So again, this piece is continuous, but as a whole, this piecewise function is discontinuous. Now, if we were not looking at the graph, not using the calculator, how would we go about... Sorry, let me just fix this because it's going to really bug. There, that's what it was supposed to be. Okay, how would we go about finding the answer here if we were not using the graphing calculator? So the possible discontinuity, the place we would have to check is here at this, gosh, I don't know what the word, the word. I don't know what the word is. The word has escaped me. So at that x value, at that possible break, do we have, the gap in the graphs like we saw, or would they flow? So if you were doing this without having to use the calculator, you need to plug that endpoint in. So let's plug in, or let's find f of 0. Let's plug, okay, 4 times the charm here. Let's plug 0 into the first piece. So if I plug 0 in here, 0 plus 1 is equal to 1. So this piece has an endpoint at 0, 1. And if I plug 0 into this function, 2 times 0 squared plus 4, then I end up with 4. So that means that piece ends at 0, 4. And so I can see at x equals 0, the limit's not going to exist. The limit of f of x as x approaches 0 does not exist, because the limit from the left, that's really driving me crazy that I can't think of this word, but the limit from the left is 1, and the limit from the right is 4. So since those one-sided limits don't coincide, again, this is a discontinuous graph. So we're going to say that it's discontinuous at x equals 0. So our interval of continuity is everything else, everything before 0, so negative infinity to 0, and then everything after 0, so 0 to positive infinity. There are intervals of continuity there. Okay, so sometimes our piecewise functions are going to be discontinuous because one piece doesn't pick up where the other one left off. So let's do something similar here. We've got 3 pieces in this graph, and I know that the 3 pieces on their own would be continuous. So this is a polynomial, it's continuous, this is a polynomial, it's continuous, and this is an exponential function, all continuous pieces. But do they pick up where one left off? So that do they connect if we put all 3 of the pieces together? So let's evaluate this function at each of these boundaries. I think that's the word I was looking for earlier. So let's plug -1 into this function. So we have 5 minus a -1, which would be 5 plus 1, or 6. So that means that function ends at, we inputted a -1 and we output 6. So that's where that piece ends. Okay. If we look at the second piece, I have 2 boundaries to input. So I need to input the -1 and the +1. So those 2 boundaries means that middle piece will start and stop. So when I input 1 and -1, -1 cubed is -1, and +1 cubed is going to be +1. So that means this middle piece starts at -1, -1, and it stops at +1, +1. Okay? And then finally, let's look at this third piece. I'm going to input 1 here. So I have 2 to the 1 minus 1. 2 to the first is 2, and 2 minus 1 is going to be 1. And so this one ends at, I input a 1 and got a 1. Okay, so now we need to look at where one ends and the next one starts, and so on. It's like continuing these pieces. What this is showing me here is the first piece ends at 6, and the second one picks up at -1, so there's going to be a discontinuity there. Those 2 pieces don't correspond. Now this middle piece stops again at +1, and then the other one picks up at +1, which means there's no discontinuity there. So this is going to be a discontinuity, and then this is going to be continuous. Okay, so I see one discontinuity, and that happens at -1. Our discontinuity happens here at -1. So we have a discontinuity at x equals -1, which means our interval of continuity will be everywhere else. Intervals of continuity will be everywhere else. So not at -1, but everything before -1. So we're going to say negative infinity up to -1, and then we're going to unite that with everything from -1 to infinity. Okay, so those are going to be my intervals of continuity there. Now I did the work, and I'm hoping that makes sense, but again, you could start with the graph, or you can use the graph to confirm your work, but if you put this in a Desmos, you're going to see basically the same picture I tried to lay out there. So let's graph the first piece. So 5 minus x, that's a linear function. We only want this for the set of x's that are less than or equal to -1. So there's the first piece. The second piece is a cubic function, so x to the third power. But this is only for the set of x's between -1 and 1. So from -1 less than x, oopsie, less than x less than or equal to 1. There's that second piece, really tiny. And you can see, again, there's that discontinuity at -1. We have to jump from the green to get down there to the purple. And then the third piece, 2 to the x power, and then a -1. Okay, so, and this is for the x's greater than 1. There it is. So now the third piece, just like we showed on the paper there with our work, picks up right where the other one left off. So if I'm looking at 3 different pieces, there's only that one discontinuity trying to trace from the green to the purple. But if I'm tracing purple to black there, there's one continuous piece. There's no gap in those 2 sections. Okay? So whether you're familiar with your function and able to spot a discontinuity or when a graph doesn't, continue forever in both directions, if you can't find those algebraically by hand, you can always rely on your calculator to look at the picture. But ideally, I just need you to see what a discontinuity is. So if you understand when you're tracing your graph, if you have to jump over some kind of a gap or an interruption, that's a discontinuity, and then tell me that everything else is continuous, then I'm good. So however you can go about getting your answers, I'm okay with as long as they make sense. All right, so I think you've got enough to get going on your assignment, but as always, if you need some help, have any extra questions, then reach out. Until next time, take care.